Hi everyone, let's continue class. So in the first part of the class, we talked about states of two qubits, and now we're going to talk about measurement in two qubits. And there are two main properties that I want to focus that uh, we, that are different from what we thought about one qubit. One of them is general for any high-dimensional system, and since you already know a lot about quantum physics, you remember, and it's degeneracy. I want to know if I have degenerate eigenvalues in my observable or not. This can happen regardless if it is a composite system or not. So for example, if you have what we call a Q-tree, a three-dimensional system, you can have degenerate. Okay, so this is one of the things I want to talk about a little bit. The other one is specific for composite system. I want to know if I can implement this measurement um, independently with each part acting on its own qubit, or if I need to act jointly on the qubits or in the system. Not necessarily needs to be a qubit. We're going to focus on qubits here, but it could be a composite system of some other system, not necessarily a qubit. Okay, so these are the main things I wanna think about. Remembering that we are thinking of measurement as an observable, if you will, but the actual eigenvalues are not that important. So you see that I'll completely ignore the eigenvalues. The important part for me is the subspaces that the eigenvectors generate. So that are the eigenspaces of the observable. Is how it, the information that I am trying to distinguish here. Okay, so it's all about the subspaces and not actually about the eigenvalues. The important thing here is that the eigenvalues are different or equal if they're degenerate or not. Or in other words, if the eigenspaces are one-dimensional or if you have higher dimensional eigenspace. Okay? And please stop me if I'm being too much mathematician. If you don't understand anything, you want me to repeat. Okay? Okay. So when you're talking about higher dimensional systems, it's quite different from what we have of a qubit. Because when we have a qubit, the observable have dimension 2. So either the two eigenvalues are different, and then you are distinguishing between two options, or the two eigenvalues are equal, which means that your observable is the identity, and it's not actually measuring anything, okay? It's not testing anything, it's not distinguishing anything. So it doesn't really make any sense to talk about degeneracy for one qubit. But when you have higher dimensionals, then degeneracy becomes an important thing to worry about. And you may have fewer alternatives than the dimension of the space. Okay? So what we call complete measurement are the ones in which you have the same number of outcomes as the dimension of the space. So for 2 qubits, the dimension of the Hilbert space is 4. So you have 4 outcomes, no degeneracy. Okay? So in this kind of measurement is the easiest one to work with because there will be no dependence on the initial state for the post-measurement state and everything. So for 2 qubits, a complete measurement is a measurement with 4 alternatives. And here I'm using A1, A2, and A3, and A4 for the eigenvalues. The exactly value is not important. The only thing that is important is that they are different. Again, This is just for the point of view of quantum information, like theoretical quantum information. When you are actually working with the systems in the lab, the value of the eigenvalues will be important, okay? But from the perspective that we have here, we are not going to look into that in too much detail, okay? So we have distinct eigenvalues, and you have the corresponding eigenvectors. Here, each one of them generates one of the eigenspaces of these observable eigenspaces with one dimension, okay? In this case, things are simpler because all we care about is this baby here. Then to compute probabilities, we all we have to do is to write the vector in this basis, and we look at the coefficients. So the probability of getting outcome AI is just alpha I squared, modulus of alpha I squared, okay? Just look at the coefficient. If the measurement was applied to this state and outcome AI was obtained, after the measurement, the system will be described by the final state AI. So I don't even have to think about to decide what is the final state of the system. It's just going to project the initial state into one of the eigenvectors, okay? Examples. Measure Z in each qubit. Measuring Z in each qubit corresponds to distinguish between these four states here. I want to know what is the value of measuring Z in each of the qubits individually, okay? Again, look that I'm not really talking about eigenvalues here. It is irrelevant, the values of the eigenvalues, but it is important that I have four distinct eigenvalues, okay? Each one of them corresponding to one of the elements of these spaces here, okay? Important. Let me just show you. It took me a long time to learn this, and I was super intrigued when I did, but it's absolutely trivial. Measuring important. Measuring in each qubit individually. It's not is not the same thing as measuring the tensors. Okay, remembering that Z also denoted sigma Z in any situation is this matrix here. So I have two outcomes for this measurement, 1 and -1. So if I measure Z in each qubit, I'm recording each of the outcomes. So I have 4 outcomes. 1 in the first qubit, 2 in the second qubit, 1 in the first qubit, -1 in the second qubit, -1 in the first, 1 in the second, -1 in the first, and -1 in the second. So you see here that measuring Z in each qubit corresponds to 4 different alternatives, okay? But if I compute the tensor Z as a matrix, so this is 1, 0, 0, -1, tensor 1, 0, 0, -1, Let's remember how we computed the tensor product of two matrices. This is 1 times the second matrix. This is 0 times the second matrix. This is 0 times the second matrix. This is minus 1 times the second matrix, which gives us 1, 0, 0, 0, 0, minus 1, 0, 0, 0, 0, 0, 0, minus 1, 0, 0, plus 1. So see what we have here. This is, it has the eigenvectors of this matrix are also eigenvectors for the measurement of the image qubit. But here I have the genericity. I have just two eigenvalues, okay? So you have to be careful when you write this kind of thing here, because when you look at it, it seems like it's a local measurement that you are acting on individual qubits, but not necessarily because of the genericity. So to implement this measurement here, this way with this degeneracy, you cannot do this locally. Okay? So it's subtle, but you have to be careful. In my mind, everything you write this way is a local measurement, but when you're implementing it, not necessarily it's going to be if you want to keep the degeneracy this way. Okay? I was in a PhD defense of, I was in the committee when I realized it. So it took me a long, long time. And this is important. It might be problematic. Okay, questions so far? Okay, so not this one, but measuring the image qubit, which was our original example. This is a local measurement, so you can implement this measurement acting individually in each qubit. And to compute the probabilities, all you need to do is to look at these coefficients here when your two-qubit system is written in the standard basis and on the canonical basis. Okay? So, simple example, calculate the probabilities of the possible outcomes to a DZ measurement for this first state. So this is completely trivial because the states are already written in the basis that we want. So here I have probability of 1 equal to 1, all the others equal to 0. Here I have probability of 0 of 1 equal to the probability of minus 1 equal to 1/2, and the other equal to 0. Let me just write it here as well. And here we have the probability of minus 1 of 1 minus 1 equal to the probability of minus 1 equal to 1/2, and the other two equal to 0. Okay? In this case, it's simple because the states are already written in the basis that we are interested in, so we just look at the coefficients. Okay? Now, next example is measure x in each qubit. So now, again, we're going to have for outcome, again, Generally, we think about outcomes as one number, one eigenvalue, but here I'm just thinking about levels that can differentiate between the possible outcomes, okay? So if you're measuring x in each qubit, you have two outcomes for one qubit, two possible outcomes for the other qubit. So the possible outcomes here, I will label as 1 minus 1, 1, 1, 1 minus 1, minus 1, 1, and minus 1, minus 1. And each of these possibilities here correspond to one element of this base. So it's exactly the same thing, but we're using the base plus and minus here because we are measuring x in each qubit. Okay? Again, this is a local measurement. I'm applying x individually to each qubit. And to compute the probabilities, I have to write the state in the basis corresponding to that measurement. Okay. Again, another opportunity is to compute the projectors for each outcome and use that that equation that we saw in the first lecture to compute the probabilities and also the final state, but it is equivalent. I find it easier to write the state in another basis, in the appropriate basis, but it might be the case, especially if you're doing this over and over for many states, that it just computes the projector, and especially if you're using a computer to do that or anything similar, you just compute the projectors once and then just use it the same equation for every state. So it depends. Since I'm just doing this for this class, I prefer to use to write the state in the correct basis. Okay. Again, the same homework, same exercise, but now with the measurement XX. And here is a bit more complicated because we need to write the state in the correct basis first or compute the projectors. Or I'll use the first option. So these two I'll leave as homework to you. And I'll do this one right now because this is more interesting. Okay, so our state is psi minus equal to 0, 1 minus 1, 0 over square root of 2. And I need to write it on the basis plus plus, plus minus, minus plus, minus 1. For that, I will remember that 0 is 1 over square root of 2 plus minus, and that 1 is 1 over square root of 2 plus minus minus. Okay, so I will write this state in the new base. Okay, so this is going to give me I'll leave the 1 square root over 2 here, another one here, and I'll have 0 plus minus tensor product with plus minus minus this is this. And now the second part, plus 1 over square root of 2 plus minus minus tensor plus plus minus. A lot of plus and minus. And this part here is this part here. Okay? Now I'll just open everything. So 1 over 2 is it correct? Okay, so now I'll expand everything. So I'll have plus 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 minus plus minus plus minus. Yeah, it's confusing. I know. Plus plus plus. There is a square root of 2 missing somewhere. I'll find out. Plus plus minus, and here there is a minus here. So this is a minus. Minus minus plus minus plus 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 minus minus plus plus minus minus. Now some of those things are going to cancel. So this cancels with this. This should be a minus as well. So this cancels out with this. There's a square root of 2 missing somewhere. Here is the square root of for one of these and another square root for one of these. So this is 2. This is 2. Because there's one square root of 2 for each one of the sides here. So this is going to give me 1 over 2 square root of 2. 2 minus plus plus 2 plus minus minus, and canceling the 2's here. This is going to give me minus plus minus plus minus. Okay, I know this was confusing. Let me just explain what I was doing. I just wanted to rewrite this vector on the correct basis and this basis here. So what I do is to replace 0 by this linear combination of plus and minus, and the same for 1. So I substitute these combinations for 0 and 1 and extend it using linearity. A lot of things cancel, and this is the final state, the same state. I'm just changing basis. Okay, so this continues to be time minus. Okay, and now I can compute the probabilities for a measurement of x. So the probabilities are probabilities of 1, 1, and minus 1, minus 1. is equal to 0, probability of minus 1, 1, and 1 minus 1 are equal to 1/2. Okay? Questions so far? I imagine you have a lot of questions about this, but maybe this only makes sense when you actually compute it yourself. So do the homework. It's really stupid and really simple, but it's important for what's to come. Okay? So remember when we saw this in here, and before we took a break, I reinforced that it's all about correlation. So if you see here, there is a correlation here on the outcomes for the measurement of Z. So anti-correlation, if you will. So I know that the outcomes will always be opposite for this state. Here you have correlation, perfect correlation. The outcomes will always be the same. Here, it's really interesting that the same state that gives correlations to a measurement of Z will also give the same type of correlations for a measurement of XX. So here we know that the outcomes will always be opposite as well. So this is the kind of strong correlation that we generally talk about when we have entanglement. So we have correlations for a measurement of ZZ, also correlations for a measurement of XX. And this state is really special because it will show the same type of correlation whenever I make the same measurement of both qubits. So this is really, really interesting. And this is going to come up later again. Okay, so now you can think about whatever measurement you want. So you can measure X, the first qubit. Oh, here is wrong. First qubit, and Z in the second qubit. So now this is going to be related to this basis here. Again, a local measurement. And to compute the probabilities, you need to write your state in this basis here. And again, if you want to repeat the homework with this, but it's just a matter of changing the basis. Again, in this case, even easier because you just had to change the basis in the first qubit. Okay? Okay, now let's go to a bit more complicated measurement. And it's a measurement that corresponds to this basis here. Remember that these vectors are entangled. So it is not possible to implement a measurement that has these states as eigenvectors locally. Okay, so it's our first example of a non-local measurement. To implement this measurement, an observable that has these eigenvectors. Again, the eigenvalues are not important as long as I have 4 different eigenvalues, one for each of the Bell states. It's really, really difficult, okay? For those of you that work in a quantum optics lab, you know what I'm talking about. You're probably already worked with it. So you can tell your friends how hard that can be. In other platforms, it is not that hard, but it's always hard because the qubits help to interact in some way in order for this measurement to be implemented. It's hard, okay? But it's crucial for quantum information. This is a non-local measurement. You cannot implement this measurement acting locally on the qubits. The qubits, you have to interact jointly with the qubits, okay? Okay, so again, to compute the probabilities, I have to write my state of 2 qubits in these phases. And again, we can do this homework here. And this is simple because here I will have the outcome corresponding to p plus equal to 1. Here I'll just label the outcomes by the label that I use for the vectors. It doesn't matter, okay? The others And here, the probability of psi minus equal to 1. The other 3 are equal to 0. Now, for this first vector here, I have to write it in terms of the Bell basis. So you can check that 0, 0 is the same thing as 1 over square root of 2. 5 plus 5 minus. So here I have the outcomes 5 plus equal to 5 minus equal to 1/2, and the other 2 equal to 0. Okay, so in this case it's relativity as well. So this is a hard measurement, a non-local measurement, but it's a building block for many quantum information protocols. One of them is quantum teleportation that we're going to see next class. Questions? Okay, there's something in chat that Enrique was helping me with the square root of 2 that I missed. Thank you. I just saw it now, but thank you. Please continue correcting me whatever I do stupid. I do that quite often, and I really need your help to see that, to correct that. This one I was lucky that I saw it quickly, but generally I can struggle a bit with really stupid things. Please help. Okay, now we have other options as well. We have measurements with less outcomes. And those are the measurements that have degeneracy, as we already mentioned. Now that we have more than two dimensions, it is possible to have degeneracy, and we have to take that into account. So now we are not actually talking about a basis, but a partition of an orthonormal basis or eigenspaces of more than one dimension. So let's see some examples. So for example, I can just measure Z in the first qubit. So I don't care about what happens with the second qubit, just what happens with the first. So now my outcomes would be corresponding to these partitions. So these two vectors. So these two vectors correspond to outcome 1 for the measurement Z in the first qubit, and these two vectors correspond to outcome -1. Again, it does not actually matter the vectors that I put here, but the eigenspace, the subspace generated by these two vectors, okay? This is a local measurement as the other one. I'm just ignoring the second qubit and measuring the first. Again, we can write it in the corresponding basis, remembering that this is not unique because now I have eigenspace of dimension 2, so I can change the basis in that eigenspace as I wish. And again, I will leave this as a homework for you. I will come back to this later. I will do some of the examples, but not this one. So important thing here that now the probabilities were just looking at one of these coefficients. And now since we have two elements of the basis corresponding to one outcome, the probability will be the sum of two coefficients. So I'll better do the example just to make it clear. So here, the probability of outcome 1. Remembering that I'm just measuring the first qubit, so I just have two outcomes. plus 1 associated to this eigenspace and minus 1 associated to this other eigenspace here. So now the probability for outcome 1 will be alpha 1 squared plus alpha 2 squared, and probability of minus 1 will be alpha 3 squared plus alpha 4 squared. Okay? Questions? Remembering that now I have degeneracy, that's why I have less outcomes than the dimension of the system. And here I have, let me just talk about the last one, just because I'm running out of time. So probability of outcome 1 is 1/2, and probability of out 1/2, there's something wrong here. No, it's okay. Probability of outcome minus 1 is minus 3 over 2 squared plus b squared. So now I'm summing this, I'm looking at these two coefficients here, and this is equal to 1/2. Okay, so now that I have the degeneracy, so I'll have to look to more than one element in that linear combination. Okay. Now we also need to pay attention to the final state, because it's going to be projected in this subspace. So now it's not going to be just always the final vector associated to the outcome, but a projection of the initial state into the corresponding eigenstate. And now this depends on the initial state. So here you see that the actual coefficients of the initial state make a difference. So we have to pay attention to that as well. And the same thing for the other outcome. So the initial state will now play a role. Okay, other examples. Measures in the second qubit now corresponds to this partition. So now it doesn't matter what happens to the first qubit, what happens. I'm just looking at the second qubit, same thing. Again, a local measurement. Again, I have to write in the corresponding basis, or I use the projectors as we saw in the first lecture. Again, homework for you. So if you go back to these slides, I will send it to you right after the class is over, and you go to these exercises. I know it's a really simple exercises, but if you're not sure, if you remember all these things, or at least you haven't seen in this notation, in this way I'm presenting to you, it might be a good thing to go through these exercises to make sure you understand it. If not, come to me, we'll go through them together, because I'll be doing this kind of calculation the entire time throughout the course, throughout the lectures. So next class, I'll just be applying this kind of measurement over and over to make a protocol, and it is important that you understood this properly. Okay, so go back to the homework and make sure you understand what is going on. They're simple, but they're the cornerstones of everything we're doing next. Okay. Again, the final states are the projections of the initial state in the eigenspaces. And because they are two-dimensional, it will depend on the initial state, okay? And the same thing for the second outcome. Okay, another interesting thing is that I'm not actually measuring Z. We talked about measuring Z in each qubit, but I could just ask if I measured Z, would the outcomes be equal or different? So I'm kind of doing a coarse graining on the ZZ measurement, and I just want to know the outcomes are equal or the outcomes would be different. So this would be corresponding to outcome equal, and this will correspond to outcome different. This is a non-local measurement, okay? This corresponds to that Z tensor Z that we were talking about, or it's related to that. I cannot implement this without making the qubit interact or interacting collectively with both qubits, okay? And you can already see that the intuition is already here because I'm asking properties of the collective system, equal or different. I'm not asking questions that relate to the individual qubits, okay? So this is a non-local measurement, the generate measurement. And again, I have to write in the basis, but I have to look at the correct coefficients, remembering that each outcome now corresponds to 2 coefficients because of the generosity. Okay, again, homework. Please, if you have any doubts about this homework, no matter what kind of doubt, I misplaced the square root of 2. Ask me, we'll go through these together next class, okay? Again, the state of the system after the measurement will depend on the coefficients of the initial state. This one is for the outcome equal, and this one for the outcome different. Again, this proportional sign here, that symbol here, is because I have to normalize the state to get the final state. I forgot to talk about that. Okay. Again, I already mentioned this, but it is important to notice that the important thing is not the vectors that appear in the partition, but the subspace generated by them. So measures in the first qubit, I use these bases initially, just because it's simpler, but I could have as well use these bases here. It will generate exactly the same subspace of C4, okay? Remember what I just care about the first qubit, and I don't care about what happens with the second qubit, okay? And in the second qubit, I use these bases in the first example, but I could have as well used these bases here. It generates exactly the same subspace of C4. Equal or different is another example. I use these here. This is clear what is the physical meaning of this measurement, but there are another way of writing or choosing a basis for these subspaces. I could have as well chosen this here. Again, homework for you to show that these vectors span the same subspaces of C4. So I could have used these. This makes clear the non-local aspect of this measurement. It's not, it is expected that it's non-local because of the type of thing that we are testing is a property of the combined system and of the individual qubits. Okay? Okay, so these are all very simple calculations, but you might have, for sure, you have seen this kind of calculation in the quantum physics courses that you had in undergrad and everything, but it might have a different way of framing exactly the same thing. So if you have any doubts, please reach out, tell me, and we work to this together, because I will be doing this kind of thing over and over and over and over. We'll be tired of it. So it's really, really important that you understand everything that happened here. I know that many of you already work with quantum information, so perhaps this is really basic for you, but especially for the students that are not working on the field already, if you have any doubts, please reach out. The course is for everyone. I want everyone to learn, and I will be happy to help you with any doubts you have. Okay. So questions? I ended like in the last minute, but at least I'm now back to the plan that I made, and I ruined it in the first lecture, but now I'm back to it. Okay, so next class will be much more interesting because we will have protocols, teleportations, redundant coding, and if I have time, I will talk about uh, deep commitment, the proof that Alice can cheat with entanglements. If not, we're going to see that next slide.